Dr. Marshall is engineering director and principal wireless architect for Google, responsible for spectrum access technology and future wireless systems. He's been heavily involved in wireless technology and policy, including deputy director for the Information Sciences Institute at the University of Southern California, a research professor at USC's Electrical Engineering Department, a contributor to the President's Council of Advisors on Science and Technology, PCAST, a spectrum study that led to the CBRS ban. He's also chair of the board of the CBRS Alliance and chairs the Wireless Innovation Forum Spectrum Sharing Subcommittee. His most recent book, Three Tiers Shared Spectrum, Shared Infrastructure, and a Path to 5G, was recently released by Cambridge University Press. And he has also authored 2 prior technical books on cognitive radio. Dr. Marshall has been involved in space communications, network protocols, and delivery mechanisms for the past several decades. At DARPA, he created and ran the disruption-tolerant networking program that built unique national security features on top of and further developed the IPN's underlying network technology, delay-tolerant networks. Prior to DARPA, he had addressed many of the IPN and DTN challenges in space and terrestrial networks supporting U.S. national missile defense. Following DARPA at USC, he was also the principal investigator for the DARPA Content Addressable Network Program, which was also based on the underlying DTN bundle protocol. So, Dr. Marshall.
Okay, thank you very much, Keith. I appreciate it. It's been a long time since we've worked together on DTN. So I'm going to talk a bit about expanding the scope of IPN through expanding the scope of delay-tolerant networking. I think this is the infrastructure of IPN, so we're going to talk mostly about this enabling technology underneath it rather than IPN itself. So this was the outline abstract you had. So in the vision of IPNSIG, it talks about promoting and increasing the maturity of DTN. And so the argument that I'm going to make for the rest of the next hour is that promotion of DTN inherently will increase its maturity. In fact, the way to get maturity is to look to see who else will adopt it. How can DTN find a home not in the niche with space, but in the underlying commercial services we use every day? Are there unique and challenges that require DTN? In a lot of cases, people may not even realize they're there because they've just thought about other paradigms for networking. And when I talk about DTN in this discussion, I'm going to be thinking about DTN not just in delay tolerant for communications delay because light speed is so slow, but more about DTN in terms of the more global possibilities of disruption, interruption, stochastic availability, in a broader set of technologies that can run on top of the same basic bundle protocol. So just, why am I here speaking about DTN? Keith covered some of this. Long ago, my job in life was dealing with the challenges of battle management, command and control. I haven't said that in a long time. And intelligence in the network architecture for U.S. missile defense. Highly disrupted networks of satellites, interceptors, ground facilities, radars. Nuclear war is very disruptive to communications. We were transitioning from designs that were built around unique and often proprietary message passing protocols to the use of IP everywhere. So we went from architectures where every node saw every message that went through it, where you could make case-by-case decisions, to thinking about how to do IP. And we were struggling a lot with those issues. Transitioning from message passing to IP is non-trivial. Good news is I left there and went to DARPA. I didn't have to solve all those problems. At DARPA, Vint came in about a year after I was there, and I talked to the director about DTN, and I was asked to take a look at that program. We weren't allowed to do open source, so we created Disruption Tolerant, and Disruption Tolerant built and looked at a variety of different reasons why networks get interrupted, all built on top of the same DTN framework, and then we could contribute code to the DTN framework. But it made us start to look beyond just the delay networks that we see in space communications into stochastic availabilities, random connectivity, mobility, and a lot of other causes that still drive you towards the same architecture as DTN. At USC, I was a principal investigator for a DARPA program. We're putting on top of DTN, the bundle protocol. We put content-based networking to think about the fact that DTNs also essentially are an automated cache. So how can I have networks that, as they distribute information, automatically provide a cache and run that across the same DTN bundle protocol? And now at Google, I'm working to create more integrations of the networks we all depend on, which is breaking down the silos between space networks, ground networks, the cellular networks, Wi-Fi networks. There was a time when they were all unique. They had roles in our lives. But today we use them so interchangeably that these silos don't make a lot of sense. So I think, question is, why should IPN care about making DTN more adopted? It's its own tool. It controls it. It kind of owns it effectively. But when we get large contributing communities, they build good, sometimes bloated, but good software. There are exceptions, but more people contributing, more people bringing ideas in, more people using and experimenting with it builds the user base that makes products. Consequently, we see a lot of the large software initiatives that 10 years ago companies would have kept as proprietary. They now push into open source and invite everyone in. Broad adoption means we'll get services available, clients available, and DTN will become more the infrastructure, much like IP is today. And they take away the dependency on any single organization to fund and deploy the service. When we were funding it at DARPA, we were pretty much the prime funder of this. That's a high jeopardy situation for any technology. So there's a lot of other uses that would really benefit from DTN. The real problem is that either people haven't thought about it, or to some extent, to think about disruption tolerant networking, you kind of have to admit you need it, that your network isn't perfect. So we'll talk about what are the reasons that people might want to adopt the DTN. So first, we're going to take an expansive vision of IPN as requiring a well-deployed, mature, and evolving DTN infrastructure underneath it, the broad adoption to get product maturation, to get more investment and more deployment. How do we make DTNs everywhere? Not unique to the space mission, but something that is a basic service of the internet, much like we think about web and IP today. And then use that recognition to bring back that flexibility into IPN. And there's three specific questions that I'm going to walk through today, and we can discuss afterwards during the questions. Who else in the world should care about DTN other than IPN? And if so, how do we convince them of this? And this is largely from painful experiences working in DARPA, trying to push DTN into more and more of the US defense missions. Secondly, is sharing the ideas and capabilities of DTN into 6G. In the past, the cellular world was kind of self-contained. It built its own solutions. It built its own networks. They were independent services. In 5G, we started to see that change. 5G has developed very sophisticated models for how application layers can interact with layer 1 and 2, piercing the traditional layers. And those are also really applicable to a number of other networking technologies. And 5G is looking for missions beyond the classic handset. Once you get 100% penetration, there's not much more you can do. And a lot of those missions are really well tuned to what we can do with DTN. And then lastly is kind of a thought piece I'd like to leave you with, which is thinking about, can DTNs be a tool to avoid a deadly embrace in what we've created, which is now an extremely IP-dependent ecosystem. Even space, it was sort of the last area where we didn't see, we saw unique physical layers, but more and more of our space-based services are themselves now IP dependent. So those are the three opportunities we're going to talk about. I want to start with why selling DTNs is so hard and the challenges to DTN adoption. So I had 13 programs at DARPA. One of them ended up with an Obama executive memoranda. But by far the most work I put into trying to convince people to adopt the programs was in DTN. Because there's so many reasons why people will not accept the idea that they need a DTN. First, we have the problem that we have so much connectivity today that people can't imagine that there are things you can do if you're not connected. I'm either connected or else there is no such thing as connectivity. And so delayed delivery, everybody kind of wants the network equivalent of Amazon Prime. If you talk to the network providers, their view is their network, their connectivity, whatever they're selling is so good, they don't need a DTN. Why should anyone need it? Because it's never disrupted. People are not thinking about information as having value after they request it. And then what's kind of interesting is the throwbacks on this is not how IP works, true, and a very, very strong belief that end-to-end transfers have to be managed by endpoints. In talking with Vince, I once commented to him that he not only developed the technology, but to some extent he developed the theology that so many generations of networkers have grown up with IP as the sole means of networking that they almost can't imagine doing it any other way. So when you talk about transfers being managed step by step through a network with independent decisions being made with persistence, with knowledge and intelligence, it really is contrary to generations of network developers. So the challenges that I found is that we really teach something very different when we talk to people about DTNs. IP teaches managed transfers are managed end to end. DTN has transfers managed hop to hop. IP was built around relatively dumb intermediate systems. DTN has relatively smart ones. IP teaches stateless intermediate systems. A packet goes through and it doesn't change the state of the router typically. And in DTN, of course, they're highly stateful. They have persistence. A bundle that can't be delivered is retained until that bundle can be delivered. And the router may learn something about the routes that are available as it sees bundles from different directions. We move from deterministic routes to situational routes. IP sits as a layer 3 network. DTN can operate over 3 or 4. It can actually work with a convergence layer. So one of the challenges in bringing DTN into the mainstream is that we really are unteaching decades of Internet protocol and TCP doctrine. And doctrines, as they live through generations unchanged, become relatively rigid. So I'm going to talk a little bit about the work Keith and I did within Department of Defense. The two boxes towards the top are the DoD version of a mobile handset. The first one's inside a Humvee. The second one, I think, is an Humvee. I'm not really sure. These are our typical radios. We wanted to show DTN in the context as close to the user's mission as possible. And the user mission that we used was one that was developed by the Marine Corps, basically mirroring their ongoing experience in Iraq. The third chart there with the green and red lines is the connectivity running around, in this case, an area in Virginia called AP Hill. I think it's probably been renamed because AP Hill was a Southern general. And as this is a KU satellite shot, and as you can see, even running around relatively straight terrain, it has connectivity coming in and out. This unit would continuously lose and gain connectivity as they went around the route we developed. And so the challenge was, how do you synchronize the status information among all these units? And in the baseline architecture, they went and used TCP to send messages back and forth. In the DTN architecture, they used the bundle protocol. And as you can see in that graph kind of lower to the right, the DTN, which is that kind of weird purplish color, using a massive less bandwidth, about 7 times less bandwidth than the core apps in maintaining the synchronization. There are other charts that we developed that actually show they were much better synchronized running in DTN. So it took 1/7 the bandwidth, and it actually performed significantly better in synchronizing. So synchronizing is a pretty big application today. Our watch syncs with our phone, or in my case, watch syncs with a tower. My phone syncs with my cloud account. My devices sync with my cloud account. So synchronization was, I wouldn't want to say unique then, but it was more unusual. Today, it is really one of the core processes of our network. And we showed that DTN really is a much better way to do this synchronization. And we got good press on this. There's Keith's paper there in the center below, and his partner Bob Durst over on the left side. And we made Defense News because it was really a great success routing around obstacles. And so there is great utility in DTN. They solve problems that otherwise can't be solved, and I think we showed this. But and it's very effective. This is just also just to show performance, DTN delivery over time versus the end-to-end. End-to-end, as these devices spread out across the area, basically just started to fail. DTN used relatively small amount of bandwidth. Again, that's the lower blue line on the lower chart compared to the DoD system, EPLARS. And the latency was much better. So all in all, it tastes great, less filling in all regards, and it's still not deployed. So the question is why? It was used in Iraq. It wasn't deployed afterwards. So when given a chance, we've shown that DTN solves a range of problems. And in order to do this, we were lucky we could create a A/B case where we could show DTN versus non-DTN. We could use metrics that were user-driven, not network-driven. And these were important, but they come back towards what did we learn about behavior here? Keith and Bob published a lot of papers about the technical performance. What I learned was non-technical. Network people don't like to admit they need DTN. They screamed up and down that, oh, we don't really need to do this. We should just use the baseline we have. It takes immediate urgency. In our case, we had the urgency of the fact that American kids are dying in Iraq because of lack of communications. That created a real incentive for people to work with us and to deploy our system during that period. But it didn't create enough to get it over the burden to actually deploy it as a baseline, because the network folks, oh, we can just fix all this stuff. So it's really hard to do that. In mobile obstructed environments, DTN is clearly superior to synchronized edge and central services versus throwing lots of IP messages back and forth. And we're going to come back to that because I think there's a real opportunity to leverage this experience when we think about how 6G is evolving. And the interest we got was largely because we were flying Vince Cerf's flag. And it's very hard for people who were very indoctrinated the IP theology of end-to-end management. We said, well, Vint was kind of the guy who put that out there. But by the way, he thinks this is a good idea too. So that was really helpful. But in the end, the belief that networks can be made to work perfectly well without these tools kind of block going further. So commercial concepts relative to DTN. I think the future is we need to institutionalize ourselves. So we should think about 5G for the moment and where 5G is going and ultimately where 6G will follow. So 5G standalone is a fundamental shift in the network design. In the past, operators thought of the radio access network as what they monetized, what they got money for. In 5G, they saw that the core, the control plane, actually was a monetizable feature. that access to that control plane, control over the control plane by hyperscalers and other users could generate revenue for the network. And so in 5G, we completely redesigned the control framework of cellular to now be essentially a cloud computing instance, just software, not hardware. And it provides the network the ability to actually interact with applications about the layer 1 and layer 2 features of the network. This differentiating feature, the control plane, allows the applications that run on it to obtain capability of the network. What can you do for me? How good is this particular device's connectivity? And so if I'm perhaps streaming video to it, I can take a look. Should I start feeding it standard definition, or can I fire right off with 4K? Because I understand what's there. I don't have to buffer 6 or 8 seconds. I can understand the capability of that device. I can understand if it'll have mobility, and it might change access base stations. And so I need to perhaps delay that transfer while I'm doing some highly important transfer. So it sort of breaks the idea that this device just sits on top and looks at an IP stream. That latter part is done by specific message flows, policies, and essentially service level agreements. I think the important thing in this is two things. One is that there's models for this ability to reach in and understand what's going on in a physical layer that are going to be commercially supported. People will be trained with them. People will have the tools to develop them. And secondly, that what we see in the cellular world is a recognition that they have to do more than just connect people to towers, and how we penetrate that. So if we look in the future, what we're going to see are bridging of networks. The cellular industry was wireless for a long time, but right now cellular is outdoors is around 10 to 15% of bandwidth. The rest is indoors. So ultimately, networks are going to become bridged. Users are going to make cost and energy driving choices rather than just saying if it's wireless, it has to be on a cellular. If it's indoor, it has to be Wi-Fi. Those choices are going to become much more subtle, and networks are going to have to be able to adapt to them. And that works to DTN's advantage. And we already see in the handset community that the handsets have been driven to have bridging behavior. That is, they flip between Wi-Fi, they flip cellular, they will connect based on cost, based on availability, based on the policies you wrote in your phone, how you want them to operate. Even though the cellular infrastructure still thinks of itself as standalone, the businesses have forced handset makers to really build a whole bunch of different kind of networks with very different features. I listed them here. There's cellular, there's the Wi-Fi, there's Bluetooth. More recently, in the last couple of years, we have near field communications, car keys. Ultra wideband is coming out now to complement that. Of course, sat nav, satellite and broadcast audio, and more recently, two-way satellite. So we now have these platforms that can now look across a lot of different physical media. They don't have to think that if it's a cellular message to start, it has to say in the cellular network. So the carriers at the same time have close to 100% market penetration. So they're looking for new usage, new things they can do. And largely they've looked sort of, if I can't sell more people handsets or bandwidth to handsets, then I have to start selling to things, infrastructures and sensors. There's a great variation in need of speed. If you look at the 5G literature, it talks about ultra low latency, millisecond type latency. But at the same time, there's a lot of applications that 5G targets that couldn't care less about latency at all. I'm going to have meter readings of water. I'm going to have temperature histories at a location. None of these really care about latency particular. They're good opportunities for DTN. They're expensive to deliver over cellular, but there are a lot of opportunities that DTN can use to deliver them economically. So what I think we should be thinking about is a two-way flow of ideas and models. DTN has created some things that I believe 5G and 6G really can use. And that is the idea of node-to-node disconnected operation where the nodes can be heterogeneous, the DTN, the convergence layers. That is unique in DTN at the moment. Conversely, on the other side, the commercial world has evolved two things that didn't exist before 5G, which is a way for devices to interact via the core and actually have the services adapt to what those devices can do in connectivity at the current state and in the future state as that device roams the network. And for the device to have a capability exposure and then to have policies that express how that device should be handled by the network that can be accepted or not accepted for a service level agreement across wireless devices roaming. We've had those sorts of things for the bulk networks that were terrestrial, but now we have the ability to start thinking about what does that mean for devices that are roaming, that are mobile in disconnected environments. So I think we have an opportunity here to think about how 5G models for capability exposure and slicing can be brought in as a way to talk to a DTN, to allow a DTN to be able to negotiate what it can do and to be able to inform devices when it can meet their requirements. There's a lot of use cases for these. I think we can show that they have a model that is similar and semantically consistent across them. And as we look, 5G is kind of defined, but 6G is in the process of being made. There's a lot of work going on to define 6G radios and millimeter wave and terahertz. But the interesting thing in 6G is probably how does it manage networks? How does it manage heterogeneous connectivity? How does it deal with small $20 sensors with little batteries? And they've tried to address that, and they're partially there, but not all the way there. And that's going to be when we talk about Sidelink. But first, capability exposure. Networks inform the apps what they can do. This really pierces the layers. Now we can have layer 1 and layer 2 insights available to applications. Again, you can think about how you might use this in video streaming. It's also a good model for how the users of a DTN can interact to learn about what the DTN thinks it can do for delivery. In a lot of cases, that might be stochastic. It might be, I've seen a way to this node every 20 minutes. I'm going to jump on a streetcar. I have an idea about how often streetcars come off. And a lot of this investment is riding on this interface being used commercially. The operators are putting a lot of money into this capability on the belief that it will have a large commercial market for both public and private networks. So we're going to see these models mature over time. Similarly, network slicing goes the other way. The application says, I need this service. I need to get this delivered in 20 minutes. It's the current temperature. That's my service agreement. Can you do it? And if the DTN has a belief it can do it, can take the slice. If it can't do it, then the device may have to use a higher cost way to deliver that data. But it brings us to the ability to think about the performance of networks as something that can be bid on, if you will, and then a contract form to deliver that data. And it has a formal semantic and a syntax that I think we can use. It works well. And so it also allows, as I said, the device, the network, the DTN to reject it. So one of the issues with DTN is, well, people don't know when it gets delivered. Now we can go and say, well, for the network to actually feed back to applications. So now you can imagine an application that might talk to the DTN and say, can you accept this mission? And if the DTN can, great. If it can't, it can just choose either not do it, or it can choose to spend more to get the traffic delivered. So one of the resistance to DTN was, well, I'm sending stuff and I have no idea what happened. That was one of the throwbacks that we got when we were out talking about adoption. Well, here's a way to solve that problem by having some confidence in delivery or being notified if that confidence will be not achieved. Sidelink is a place where I believe DTN fits beautifully into what 5G attempted to do and what 6G will. And I think one of the takeaways I'd like from today is that we have a real opportunity, I think, to embed DTNs as part of the more broader framework that SideLink attempts to create. So SideLink has been around since the days of LTE, and during LTE it was called D2D, device to device, and it allows a LTE device to send something to another LTE device. So you could, for certain devices, go from a handset to a handset and create a self-forming network. The idea was that it would allow a low energy device, perhaps that sensor with a very small battery, to be able to relay data through a higher powered device, a more connected device. So my temperature sensor that I've used as an example might see someone walk by. They would see that they had a phone, it had a reasonable amount of battery. They would send that piece of temperature recording to the phone. The phone would then relay that back because the phone has a larger battery and has a bigger transmitter. And so it's essentially creating this very, very low energy edge network. The problem is that they've defined SideLink in a way that is totally constrained to the operation of cellular networks, the protocols of cellular networks, and to deliver stuff within the cellular networks. Now, several years ago, perhaps 10 years ago, it was reasonable for the cellular world to view itself as kind of standalone and self-contained. The deep deployment of Wi-Fi everywhere really undoes that assumption. In many cases, the best way to deliver that might be to make one hop on cellular and the rest of the hops on Wi-Fi. It could be that it runs GS, could even go to one of the messaging formats. There's all sorts of different technologies to deliver that message. And so thinking what SideLink attempted to do, which was to create something that looked somewhat like a DTN, although it was still end-to-end, the right way to do that is really to plug in a DTN. Most importantly, there are more networks than just cellular. So the DTN convergence layers give us the ability to jump off of that 3GPP device, go over to a Wi-Fi network that gets it delivered, to go from a 3GPP to a 3GPP to a Wi-Fi, and essentially put together a delivery path that is appropriate and the least expensive by whatever network metric you want to use. The DTN convergence layers provides the authentication, the security, and the managed delivery that really isn't present in the message passing protocols that are in SideLink. It provides an open standard that is not unique or tailored to just the one industry. It's more broadly adopted. You can go Wi-Fi to Wi-Fi, you can go Wi-Fi to cellular, you can go cellular to Wi-Fi. And it's not inconsistent with reversion to a cellular only DTN cut through routing. So I think there's opportunities here now that the commercial wireless industry looks beyond handsets and starts to see things. It starts to see that I might be under a base station, but I don't have the energy to reach it. I want someone else to do that for me. This is walking towards the same kind of challenges that DTN, disruption tolerant networking, has. And I think it's a real opportunity for us to get a broad adoption and essentially think of DTN agents more broadly distributed. So there's a lot of examples of DTN networks where people sort of hop on moving platforms. So one model, of course, is I relay through networks. I think some of the really interesting work that we've sponsored in the DARPA program and has been done by other efforts is the use of physical mobility in addition to network, so-called message ferries. This is the UMass diesel network. They published a lot of work on it after our funding. And they run vehicles all around UMass, getting people on and off, and then picking up messages and dropping them off at different locations. 100% delivery, 80% utilization, even though there's only connectivity about 20% of the time. So it's a really interesting way to solve delivery challenges in locations where there's no connectivity. Even with high-powered devices, where the connectivity is expensive, where the connectivity is blocked, where I don't want to necessarily put up the kind of antenna, power source, whatever it requires to obtain the connectivity. And in DTN, the DTN community has worked for several decades on creating the open standards that are operator and technology agnostic. I think that 20 years, Scott, you can tell me if that's right, Keith, but that 20-year history has really develops a product that's really ready to be dropped in. 6G needs new ways to monetize new services. The cellular business is pretty much what it is. And so they need to find this, and I think we have something to offer them. So there's a couple things for commercial wireless I think we should be thinking about. How do we bring application policy, control, and exposure? 5G has a model for that. It's going to be adopted. It looks like it's appropriate to DTN, and it solves many of the challenges that people have brought up with, I don't want to rely on a DTN because. Secondly is the use of disconnected, episodic, and heterogeneous networks. DTN was here first. It was a logical extension of what cellular industry is already trying to do, what it already believes it can monetize in Sidelink as we move into 6G. It faces a not invented here challenge. It took a while for cellular to admit that IP won. It took really until we got to fourth generation. But this can be overcome. It will take work, but it can be overcome because I believe DTN is a much more mature, much more generalized, and much more economical to use alternative than where Sidelink technology is today. I want to leave with one thought piece, and this is thinking beyond mere disasters. This was a process or a question that was brought to a number of us, Vint, myself, some other people at Google, some academics, about how do you recover the ecosystem that is the internet, the cloud compute, the electrics generation system. If something happens, it truly takes them down. How do you bring all that back? How do you learn what's there when the systems you're dependent on aren't present? And so monolithic ecosystems inevitably collapse. They have no resilience to the lack of diversity. And so we know in history that when someone community plants one kind of crop, it inevitably has an epidemic and plague, Irish potato famine, other example, crop blights, forests that have one kind of tree inevitably end up with whatever parasite kills that tree. Towns that are dependent on one industry, one company, inevitably have a failure of that brings them down. And so we've seen this a lot in other areas, but there's no reason to believe that technology ecosystems are any different. That when we depend on a single technology to solve all the problems, we open ourselves up that any failure of that technology makes everything else in that ecosystem fail. The lack of diversity, there are no options to solve problems, ecosystems fail. And to some extent, I would argue we're kind of doing that. The success of IP has actually created a monolithic ecosystem for communications. IP has essentially crushed every other communication modality. If you think about how did people think about communications 20 years ago, you might sit and think, am I going to use ATM? Am I going to use frame relay? Am I going to do this I could use a long distance telephone. I could have ISDN. Circuit switching still existed. All of these have been essentially crushed and replaced by IP. I've talked to people who say, well, that's not really true. Look, I have a voice call. See, I got a telephone. But we know those are now VoIP. They're dependent on the IP infrastructure to operate. And so what we've done is created a system where every modality we have for communication essentially inherits the dependence on IP. That not only is for communications, but it's true for other sectors. So in the example that was brought to us, was like energy. How do you restore the grid? Well, you call people up on the phone. But the grid itself is needed to power the networks that operate the IP that uses the phone. So if you take down the power, or the internet eventually goes down, you want to bring it back up. How do you do that? And so it's kind of an unfathomable problem. It's so big, it's hard to think about. It's considerably worse than thinking about how to run a nuclear war from my prior life. But I think DTN is a part of this. I think it's something we should be thinking about also as we think about where does DTN fit into the broader picture. So the infrastructure recovery depends on IP. As I said, many people may think they're using modalities that are independent, but they're in all likelihood are not. We're not going to go and build separate COM networks just so that they are redundant with IP. Just no one's going to invest in that. IP itself is dependent on things like power. Cooling water is a big item in the data centers. Recovery is dependent on both. And so if you were starting to recover the network and you wanted to build BGP and all that, what would you do? You'd want to know who's there, who am I connected to, who are they connected to, are they up and running, are they not up running, what routing's available. But I can't do that without power. The power people can't do the restoration because they can't get the coordinate, bringing up the grid, doing the synchronizing the phases of the different generators. So we're all kind of in this deadly embrace. And so I think we should think about DTN here in the larger concept of what can we do to help society here. Primarily focused on exterior routing here. DTNs create connectivity without advanced knowledge of the topology. To some extent, this is where I was 20 odd years ago, thinking about I'm in the middle of a nuclear war. I'm seeing things fail. I'm seeing paths interrupted by plasma. I don't really know what's around me. I don't necessarily believe that things that I can't see now won't come back because they'll go through upset or they were blocked by links. And so I'm going to constantly have to be probing my network and seeing what's going on. This is a great application for DTN. If we have flooding, the bundle sentry or agents, I send a bundle to someone. They sit there until that bundle can move on further. I learned something about that connectivity. It's not duplicative of IP. It can sit on top of IP. It can use the convergence layer, so I'm not having to build a whole new digital service for it. And I think it's useful for other services, even when it's not challenged for infrastructure restoration. But I think it provides an opportunity to build in the ability to discover where we don't know. It's a much bigger question than DTN. But it's worth thinking about, and we're thinking about another rationale for really pushing DTN to play a larger role in the broad area of network operations. So with that, I thank you very much. I am obviously a strong believer in DTN. I'm a believer its benefits come when it's when widely applied. It's great to see it applied in space and to solve the delay issues of networks. But I think there's a lot it can do to solve much more fundamental problems in networking as we move to this really heterogeneous mix of very low energy, high energy, cloud-based, localized, smart cars, smart cities world that really requires a much richer set of techniques than those that are available in just in IP. So with that, I thank you very much. And Keith, with any questions you've got collected, let me know. And I'll
Yeah,
stop.
so we've got a couple of questions in the Q&A section. I've been trying to collect questions off of the chat as well. But sort of one that goes to a sort of a recent exchange on the chat window seems to sort of center around what's there are many regions of the world that seem to want internet access that don't necessarily have it if you go into remote areas. And there are systems being built. There are systems being built like Starlink or other things that are trying to extend access there, what do you see as the trade between pushing more backbone and more access into areas versus leveraging something like DTN and message ferries to getting data in and out?
So I think we should never turn our back. If you can get a Starlink terminal and you can get it through the trees, take that. We shouldn't be competing the technology for solving connectivity. What it does do is gives you the ability that when you're down in a city, then you can't get Starlink because you don't get visibility upwards. When you're in tree areas, you don't get visibility. So particularly if we move beyond thinking about eyeballs, I mean, the first step is to get connectivity to eyeballs, and all those, Starlink, those techniques are certainly more appropriate for that. But as we move to wanting to instrument, doing temperatures, water height, wave height stuff like we might have watched during the hurricane when it came into Florida, we start to move to the richer telemetry in our world, then we can't put Starlink antennas and pizza boxes on all of those. And so we have to think about how do we build networks that have a very low energy edge, and at the same time have the ability to make use of that communications infrastructure so it looks more like layers. And so I think because broadband and reading phones and the web have so dominated our connectivity experience, we tend to look at everything as a broadband problem. And yet solutions of environment, of weather, of traffic congestion and such probably lie more in automated instrumentation and sensing than in broadband. So I don't see them as competing. I wouldn't take money away from broadband to do DTN. I think they solve very different problems. I think it's just important to realize the solution is not to take broadband techniques and try to push them down to a $10 sensor. They're unique problems, and I think DTN provides that bridge between them.
Excellent. Thank you. A question from Oscar Garcia from the IPNSIG Projects Working Group. What happens with the back and forth act of DTN in database replication and synchronization? What is your experience on that?
Actually, you probably have the better experience on that than I. You built it. I'm happy to share that question with you.
Go ahead.
No, I mean, yes, there is back and forth. We've built very chatty protocols in the past. In this case, we're doing a time-stamped update. They may arrive. There may be duplicates. You don't want to do a for-exchange TCP setup operating across the DTN. And so you could think of it more as a UDP update. But the DTN is providing reliability on the handover, but the data itself looks like UDP in that it is a broadcast to the other node. Does it work as if you were fully connected with Starlink? No. Was it massively better than what was there without it? Yes. Was it totally usable by the customer? Yes. But it is a compromise. But where the choice is, I lose sync completely, and in their case, potentially lose people, or I accept that there's going to be a little jitter in the results, then I think it's very useful. But yeah, you clearly don't just take the synchronization mechanism and just put it over DTN. You have to build a different kind of client that essentially bundles those updates, has some way of deconflicting them, and then sends them across DTN. You built that code, as I remember.
So we did the DTN piece of that. There was another company that did the application layer proxy for C2PC. The results that Preston was talking about earlier, the 7 times bandwidth reduction, were actually from an application that was doing command and control, so Blue Force tracking, and its job in the world was database synchronization. And by building an application layer proxy the way that C2PC had been done was over TCP, and it had all of these issues with if you cause that TCP connection to drop, it would take it a long time to get resynchronized, and then you'd go through a big resynchronization event. Whereas with a application layer proxy that would terminate that TCP connection, move the data over, and use bundle protocol reliability, we could keep it from having those huge synchronization, having to do large resynchronizations, and get away with doing smaller ones, and that caused it to behave much better.
Yeah.
One from Stamo Grasic. We got a few more minutes. Thank you for your excellent presentation. As an individual striving to implement and apply delay-tolerant networking to enhance my private services, I've identified two significant challenges. The first pertains to the maturity and reliability of the existing implementations, and the second involves developing an effective routing and forwarding mechanism for sharing the contact graph across diverse DTN regions. Do you agree with these observations? And if so, could you please provide insights on how to effectively tackle these issues?
No, I'm here to argue you need to have more people doing exactly that, rather than to say I'm doing it. I think there's a lot of different ways to do that. We built some in our own applications. I think they tend to have application-specific characteristics to them. Satellite Keplerian is clearly the simplest because it's predictable like a watch. At the far end, you have completely stochastic availabilities that might be purely random. But I think that's the whole argument or the whole premise of this talk, is that the way to solve these problems is to have lots of other people helping and looking at these applications and looking particularly at how, as we build very specific things, and that's what we tend to do in software. We tend to solve single problems. We learn a lot about the general. I mean, we'd like to say we go from the general to the specific. Reality, we build everything twice because we really go from the specific and we learn a lot, hopefully, and we apply it to become more general. And so the interfaces for policy, the interfaces for capability are what people have kind of learned from a large amount of time. And they have generalized them as a general interface into wireless. We similarly need to be doing that. I don't have the answer. If I did, it wouldn't be fun at all to try to solve it. But I think that, I'm not going to argue that the solution is to have a lot of people working on it, and then learn from those people. So, I mean, congratulations on working DTNs. I was proud when I got mine first up and running. But I think it's a matter of having so many use cases that when we start to look at them, we can start to see how they themselves form graphs. And these are really similar problems, and we can encapsulate these kind of problems and build a general treatment that everyone can use. And I think that's why it's important to have a community, a larger community beyond just research. I mean, researchers are good. Industry dumps money and it dumps innovation, and it can do lots of trials. And so I think finding ways to fit it into the wireless architecture so it becomes really critical to people and beneficial is, I think, the way to solve those. Other than that, it's a great topic to write papers on. I don't mean to be as a flippant answer, but it really is the different varieties of solutions are so vast. I don't think it's hard to solve it for any one case. It's hard to see have I built something that works for everybody, or if it works for a large class of problems.
So I've got a separate question from just myself. What do you see as sort of what are some of the things that you think you could do with routing that is sort of in this gray area between the completely scheduled world and the completely stochastic world? Are there particular environments or requirements that you know of that would benefit from interesting kinds of routing decisions that DTN can support that maybe IP couldn't?
So, the thing that's kind of exciting when I was playing around with this in terms of packaging it as a proposal into the 6G world was, in fact, how much of AI learning can be done for the stochastic ones. Because there's very few things in this world that are truly stochastic. They all have patterns. They're just sometimes hard for us to see. I mean, the whole post-quantum computing problem is random number generators have more patterns than we would like. So even they have patterns. Buses going by have patterns. They have patterns with the day. They have patterns whether it's vacation. They have patterns with the weather. They're really hard for us as humans to learn, but we have incredible tools with deep neural networks and all now to find those that we never saw. The inexplicability of AI solutions also means that we shouldn't feel bad as humans if we couldn't find them ourselves. And so I think a lot of the stochastic availabilities, which really have some patterning, buses going by me has a pattern, days to day are different, but in general, Fridays, no one goes to work and the bus goes faster. It will learn that. It will learn if it's raining, the bus is slower. It will learn to tap that data source. And so it will find these things for us. So I think bringing AI and DTN together will provide answers to a lot of the problems that 20 years ago really flexed us. The pattern is there. We just have to find it. And plus at Google, and we're kind of into the AI thing.
One from Lee Torgerson at JPL. What can Google do to create Android DTN implementations and applications to start socializing DTN with the public? Okay,
so let's take that to what can cellular phone manufacturers do in general? So look, I mean, I think the problem that happens because customers demand it. And so it's a chicken or the egg to create that hunger that then drives that kind of innovation. I mean, we put them on there are a number of Android implementations of DTN. I know I open sourced one when I was at USC because we used all Nexus phones that ran in the Android kernel. I think the real challenge is that we start to think about an infrastructure that they can access. That's why I particularly see 6G and Sidelink to sort of go to that corner and say, you have the right idea, but let us show you the right solution. Here's a rich solution. It's independent of platform. It's well supported by standards. It's been experimentally verified by all the people who have gone and done the experiments. And it really addresses the modern world, which is not that I want to be in a cellular world or a Wi-Fi world and I pick one or the other, but I want to make the best use of all of them. So I think we have a strong case for bringing it in, but not as an outsider and not breaking down the doors, to become part of the infrastructure that makes the next generation of wireless work.
Cool. We're about at the hour, and I know that Laura has a couple of slides that we need to go through at the end here. You can all these and the other IPNSIG Academy keynote events are available from this link. If you've got particular questions about one of the presentations or material, if you email the secretariat at ipnsig.org, they can either help you or try to point you in the direction of someone who can. We've got a number of upcoming talks, the dates of which are all at this point TBD, now that we've gotten through this talk by Dr. Marshall. But if there's something there that interests you, watch the ipnsig.org page for the announcement that is going to come out. And finally, if you want to become a member of IPNSIG, you can join by sending a message to the membership at ipnsig.org, and that membership mechanism can go through the Internet Society, now that we are, in fact, despite the name, an actual chapter of the Internet Society, and the pie graph over on the left is showing the sort of the distribution of folks in IPNSIG. We've got good coverage across a lot of the world. but we could certainly use more coverage and deeper, as a lot of the conversations in the chat have brought out. And finally, if you could take a few moments, the QR code and the link that are on the screen now will take you to a short survey where you can give your opinion on the IPNSIG talks. And I think that's it. I'd like everybody to, we could all thank Dr. Marshall. Thank you very much for taking your time to do this. We really appreciate it. I think that it's the perspective there is always good, right? Always good to broaden sort of our aperture on what we're looking at as potential applications and ways to bring in the wider community and use that as a way to cause more uptake of DTN sort of throughout. So thank you very much.